So I think actually I've got a real challenge here because, as often I do, I think I was a little over-optimistic in what I could cover in my abstract, given I have 12 minutes. But I will do my very, very best. So I'm going to give you an overview of the Pliocene Model into Comparison project. I'd like to acknowledge Harry Dalzett, who's the co-leader of the project, and also all of these other very wonderful people who have helped scientifically to contribute to the overall project, and of course to the Plymouth 1 and Plymouth 2 participants, for which I wouldn't have anything to talk about otherwise. So they've done a great job. So Plymouth, Pliocene Model into Comparison project, it was a success. And let's just leave it at that. We had 8 modeling groups in phase 1. We published over 50 papers on all sorts of different aspects of the Pliocene, which I'd love to have the time to take you through individually today, but I can't. So we published papers on the monsoons, on the nature of the AMOC, on looking at the energy balance, on ENSO, and looking at data model comparisons for both the terrestrial and the marine. And I'm showing you here one diagram, which is a result from Plymouth 1, which is a nice summary diagram, which was included in the IPCC fifth assessment report. And it essentially shows 2 plots, the top one for sea surface temperature anomaly, the bottom one for surface air temperature anomaly, and then the background shading is what the models think goes on in terms of the multi-model mean, and then the point data is actually the proxy data. And the larger the circle there, the greater confidence the data community had in the data that they had from that particular site. So you can see a lot of areas where the model and the data anomaly is quite similar. However, one thing that will stick out to you is that as you move to the higher latitudes in the North Atlantic and also into the higher latitudes in continental Eurasia, you see that the models have a tendency to underestimate the magnitude of the change. So that was one of the key findings, and really that was one of the things that informed our thinking as we moved forward to the second phase of the project, which is running now. What could we do? What was it potentially about the experimental design in terms of the boundary conditions that we had within the model, or what was it about the data that we were using for evaluation in itself which could have a bearing on that, and how could we address that in phase 2 of the project? One of the things in terms of the data side, before I get onto the boundary conditions, one of the things that we have increasingly recognized is that it's very dangerous to talk about the Pliocene in a kind of a homogenistic kind of way. You know, you say, the Pliocene was like this. Well, what the hell do you mean? I mean, the Pliocene's over 2 million years, right? So that's a long time, and there's plenty of variability going on during that time. So even the question, what is the Pliocene, is actually quite challenging in that context. And as Eric Wolf so eloquently showed in his presentation yesterday, no one interglacial is necessarily like another. And so our Quaternary colleagues don't say, well, the Quaternary was like this. They say stage 11 was like this, and stage 7 was like this, and we can't carry on saying the Pliocene was just like this. It doesn't make any sense. And we've shown this sort of thing by doing modeling. So we've done orbital sensitivity tests around 2 different particular intervals of time. Orbital experiments around 3.205 million and also 3060 million. And then basically you produce those simulations, you can difference those two, and that's the difference that you would see. And I would argue, this interglacial is significantly different from this one. And so in terms of actually moving forward and further understanding how well our models are actually doing in terms of reproducing Pliocene conditions, we've got to do something about where we are in time. So here's a delta 890 benthic record going back for about 1 million years through covering the Pliocene. And there's a few things here that I'd like to draw your attention to. So here's the old PRISM 3 time slab that we had here, about 300,000 years. The data that we had for a model evaluation was sort of like an average condition for that 300,000 years. Didn't really think about the variability as much as it potentially could. And you can see we've got some big events going on in this overall period. We've got things that we would actually potentially classify as glacial periods within this overall warm phase. So what we decided to do moving forward into Plymouth 2 is to collapse this window down into a time slice around 3.205 million, which had an orbital forcing which was very similar to present day. So that's the overall strategy. Now, within the science plan, that's evolved as well. We're being more ambitious this time than we were last time. So we have a structured approach in two hemispheres here. We have experiments which are particularly focused in terms of using the Pliocene to understand the future. And we also have other experiments that are there because one of the reasons that gets us out of bed on a Monday morning is we just want to understand more about the Pliocene. It's not all about the future. So we have a mixed kind of thing here, what's shared with a single core experiment that everyone must do. That's the standard experiment. So in this hemisphere here, we might have CO2 sensitivity experiments, taking into account the fact that we don't precisely know the CO2 forcing for the Pliocene. And so there, that's in the kind of the model evaluation side. We have a CO2 uncertainty. We can take that into account. We can compare that against the data, see how we do. And also we have some experiments here to enable us to look at climate sensitivity in a slightly more rigorous way. Then in the Pliocene, for Pliocene section, we again have CO2 sensitivity experiments, but we also have some experiments where we try to deconvolve the individual contribution to the warming derived from the individual boundary condition changes. So we're up and running. The number of modeling groups has doubled from 8 to 16, which we're very pleased about. The Pliocene is now a CMIP6 experiment. And if you'd like to know more, there is a Climate of the Past special issue on PLIMIP2 where the papers are beginning to emerge, and there are some already published. So obviously collapsing down to a time slice means we have to be much more careful in the way we think about stratigraphy. And this is a paper which has just literally come out a couple of days ago by Harry Dowsett, where he's presenting a kind of a confidence rubric in assigning the use of different proxy time series to be able to get us information for this particular interval of time that we're now interested in. I won't go into too much more detail, but just to show you that in terms of thinking about confidence in the proxy signal, we're also thinking very much in terms of the confidence in the stratigraphic association. Here's a quick teaser for the proxy data that will emerge in the near future. So here's some sites which are being looked at in the North Atlantic. And here we have some examples of the multi-proxy sea surface temperature records, which Harry is working up at the moment to be able to enable us to address this question in greater detail. It's not just the marine, it's also the terrestrial that we have to think about, more challenging in terms of stratigraphy and correlation, but we're still doing it anyway. Here's some data from a site, marine site, which is telling us something about vegetation in Norway. And this is from an old paper by Deborah Willard in 1994, showing how she went through this at a pretty coarse resolution and just decided that essentially it was just all pine trees through this particular interval of time. However, Sina Panitz has just recently published a very high resolution record for this particular site. And so now actually we understand that we're not just dealing with one potential biome type, that we're having variations between cool, temperate, and boreal types of vegetation. And so this is the sort of information now that we'll be able to bring in to the data model comparisons that occur within PLIMIP2. So the boundary conditions are completely different. There's nothing which has remained from the first set. We started off by saying, well, maybe we'll just do a mild modification, but in the end we ended up changing everything. So we have a brand new paleogeography, and this has been produced in a far more sophisticated way than we were able to do before. It's done by Dave Rowley, and also Aisling Dolan was deeply involved in this as well. So we start off with the Itopo 1 bedrock. We GIA correct that, taking the ice away. We then replace the Pleistocene fill, calculate the dynamic topography component for the particular interval of time that we're talking about, figure out what we wanted to do with the ice sheets, and then put those ice sheets back on again. And then we come up with this overall topographic reconstruction here. And some of the key differences that we have here between this and the one we used previously, we have a closed Canadian archipelago up here. That is closed. We have a closed Bering Strait, and we retain the closed Central American Seaway. Now, our approach to defining the ice sheets was also more sophisticated than we did in the past. I'm sorry, but in PLIMIP1, you had to just trust Hadley Center group output. So this were just ice sheet sensitivity experiments that we'd performed in the past, and you kind of had to take our word for it, that's what we got. Well, we took a slightly more sophisticated approach now, in terms of looking at that, looking at a lot of different ice sheet model intercomparison work, looking at outputs from different ice sheet models and ice sheet models forced with different GCM climatologies to give us a better idea about where we were more or less confident we had the presence of ice on Greenland. And so that has been used to inform the PLIMIP2 boundary conditions. So we have ice centered on the highlands of East Greenland. If you want to know more about why we didn't put it on the south, I can tell you later. Also the same for Antarctica as well. So again, we've had, through the Pliocene Ice Sheet Model Intercomparison Project, people like Bastobor and colleagues working a lot looking at ice sheet model uncertainty and reproducing the East Antarctic ice sheet during the Pliocene, and also taking note of the more recent modeling studies that have come out from DeConto and Pollard, which seem to all point towards the fact that marine incursions, retreats in the marine basins of the Wilkes and Aurora subglacial basin are possible. And so in that sense, that was not too dissimilar from what we had in the first phase of PLIMIP, and so that's actually one of the things that's remained. So we've lost the West Antarctic ice sheet, and we have reductions in the margins of East Antarctica. So that's what the overall land-sea mask looks like with the ice imposed on top, and that's what all the model groups are running with. We've had other enhancements as well, which I don't have time to go into in terms of the development of soil and lake distributions, but I can't do that today. There are initial science results coming out already about the effect of those fairly significant boundary condition changes associated with the gateways. So this is a sensitivity, a PLIMIP1 sensitivity study, I think, which was completed by Betty Otto-Bliesner with the NCAR model. And what she did here was basically to take a PLIMIP1 experiment and then make these critical changes to the Canadian archipelago and also the Bering Strait, and to see how this affected the modeled ocean circulation, the overturning strength in the Atlantic, and the sea surface temperature, the amount of warming that you would actually achieve here. And what she found that essentially when you closed the Bering Strait and the Canadian archipelago, you actually warmed up the North Atlantic in a way that was actually more conducive, more consistent with the proxy data records that we actually had previously. So we've done something here that, at least in this model, moved us in the North Atlantic into the right direction. But there's more than this as well. So we have another paper here on results here from left, which is from the MRI model from Japan, where again they've imposed PLIMIP2 boundary conditions, again taking these critical gateways into account. And one of the key plots I'd like to show you here is this plot down here where they show the areas of the world that they have larger errors or smaller errors compared to PLIMIP1 and compared to the proxy data. And again, we can see here that it's moving things into the right direction. Deepak is going to talk straight after me and talk more about the results of his model, and I think you'll see more complementary evidence in that sense. So, in summary, would you trust these people? Would you trust these two? When have we ever sent you wrong? So, through a lot of hard work, we've all achieved a great deal in PLIMIP1. I think PLIMIP2 represents a significant evolution in our approach in terms of the modeling and the data that's been done. New boundary conditions and new proxy data sets, new models and new participants, a new science delivery plan. And I think it really does show what can be done when you have modelers and data collectors that are working in a very synergistic way. And I think things are going very well. A huge thank you from me and also for Harry for all of the people who've done as much to contribute to the project so far. Blue skies and calm seas ahead. Thanks very much.
Can I ask Alan whether Betty's model experiments remove totally the data model mismatch in the North Atlantic? Or is there still a mismatch?
It's a move in the right direction. Okay. Yeah. Well, I mean, one of the things that we obviously have to take into account of is that those data model comparisons are to the old time slab proxy SST data, okay, which still has those other issues that we were talking about. It'll be very interesting to see how those new model runs compare to the time series data for the slab. Yeah.
Hi, and good afternoon. My name is Deepak. I'm a PhD candidate at the University of Toronto. My supervisor is Dick Peltier. And I would like to begin by just putting my acknowledgement slides up. Thanks to Pages for funding this trip. Thanks to the University of Toronto Centre for Global Change Science. A lot of the computation that you will see, almost all the computation has been performed at Compute Canada and SciNet. Part of my salary, I guess, has been paid by Nuclear Waste Management Organization, and thanks to PlyMap2 too as well. So today I want to talk to you a little bit about some of the results that have come from an extensive set of calculations that we have performed at Toronto in order to understand Pliocene for the PlyMap2 program. So because I was expecting Alan to talk about the Pliocene and PlyMap2, I have sort of excluded that from my talk, and I'm going to go straight to my simulations here. So these are the PlyMap2 simulations, and they are categorized into control simulations, Pliocene simulations, and sensitivity simulations. The control simulations are characterized by the modern land sea mask, modern topography, modern ice sheet, and modern vegetation. And the Pliocene simulation, denoted as EOI, is characterized by all Pliocene boundary conditions. The sensitivity experiments EO and EI are designed to assess the sensitivity to changes in orography, Pliocene orography, and Pliocene ice sheet, respectively. And then finally, there are many different CO2 variations of these experiments. Going forward, I'll talk about the 280 ppm control as PI, the pre-industrial, and the 400 ppm control as modern-day experiment. And my typical Pliocene simulation will be EOI 400, that is 400 ppm Pliocene. Now, these are all the set of experiments in PlyMap2, but not all participating groups are required to do most of these. In fact, most of these are optional. But at the University of Toronto, we have decided to do almost all of these experiments, as I'm going to show you here. So these are all done with CCSM4 1 degree atmosphere and 1 degree ocean coupled climate model, and these are the lengths of these simulations. The first 4 experiments, 2 control and 2 PlyMap simulations, are discussed in a paper that has been submitted to a special issue of Climate of the Past, which is under revision right now. And the rest of the paper simulations, the sensitivity studies, will be discussed in an upcoming sensitivity paper to be submitted to CP as well. So these are some very extensive calculations with a 1 degree model. This is not T31. This has amounted to 19,000 model years of simulation, which is almost like doing a full PMIP deglaciation experiment with 1 degree resolution. This is the most extensive modeling effort at any university ever undertaken. This has cost about 364,000 core hours of simulation time and produced 300 terabytes of data. An irony of simulating climate change for saving the climate is that they produce a lot of CO2 because they consume electricity. So in Ontario, we are fortunate that 85% of our electricity comes from nuclear and hydro, so this is only 70 tons of carbon emissions, but that's still about 80 round transatlantic flights. And this could easily be much higher if you're in a different region. But speaking of electricity, this has cost us about $171,000 in electricity costs in Toronto. So this is our contribution to PlyMap2. That's like one Porsche 911 turbo. That's a very good car. So going forward, what I'm going to do is I'm going to talk to you about, well, I'm going to skip over that thing. So here I'm showing you the PRISM 4 boundary condition as implemented in CCSM4 model for the full Pliocene case here in the first column, the ice sheet sensitivity case, and the orography sensitivity case in the last column. And in the bottom row, I'm showing the orographic anomaly with respect to modern. As you can see, for the full Pliocene case, which is this one here, the anomalies are over all parts of the world. But in the sensitivity simulations, the anomalies are only in certain very restricted regions. This is the way the model was simulated. Now I'm going to talk to you a little bit about some of our simulation results, and that will take me into talking about Northern Hemisphere winter pattern that we want to talk about, and then if I have time, I'll talk about the sensitivity simulations. So the thing I want you to take from this slide here, which shows the sea ice anomaly, is that of the Pliocene with respect to PI and with respect to modern for each of the simulations, is that the maximum sea ice anomaly occurs in the critical region, season of September, October, November, the fall season. There is sea ice anomalies in other seasons too, but the maxima happens here. I wanted you to just keep that in mind going forward. So now, just briefly about a data model comparison for SST. The scatter points here show the PRISM 3 SST reconstructions for SST anomalies with respect to PI. On the background is our simulated SST anomaly with respect to 400 ppm Pliocene. And the better way to understand the comparison is through this figure here, which Alan already showed you. In both the figures here, the PRISM 3 sites are plotted as a function of latitude. So I've condensed them zonally and plotted them as a function of latitude. And the scatter points with the error bars in each of these plots are the PRISM 3 data points in 3 confidence categories. And on the left-hand side, the black dots show the CCSM4 model's response with the Pliomap 1 boundary condition. So that's the previous generation Pliomap 1. As you can see, the response of the model is fairly flat throughout the range of latitudes, and so is the response of the multi-model mean, which is shown in black squares. But if you see here on this side, where my 400 ppm and 450 ppm Pliocene simulations are shown in blue and green dots, they are warmer throughout, and the simulations are able to capture an uptick in warming at a higher latitudes, which is resulting from the new changes in Pliomap 2 boundary conditions that Alan talked to you about. So this has not been shown before. This is for first simulations to show that this is possible with the new boundary conditions, and we are very excited to have this result. The surface air temperature is shown here. These are the anomalies of the Pliocene simulation with respect to PI at top and modern at bottom for the annual anomaly, and this is the zonally average anomaly. As you can see, the anomalies are fairly high in the polar regions, but if you control for the CO2, that means if you compare your Pliocene to 400 ppm modern, that means there is no effect of CO2. You get the green curve, which shows a more balanced response through both of the poles. And now, if we look at the seasons here, then I'm showing you the 400 ppm anomaly with respect to PI for DJF and JJA, and here in the bottom row for the DJF and JJA anomaly with respect to modern. Now, immediately what pops out at you is the fact that the DJF anomaly with respect to modern is very cold. There is a kind of there's a strange feature here that the continents are colder here. And I'm going to talk about that feature for the rest of my talk. But before that, I want to talk to you about a little bit about the temperature difference in seasonality. Now, in all of our controls, 280 ppm control or 400 ppm control, the JJA minus DGF temperature difference was 3.5 degrees Celsius, but in our Pliocene simulations, it's 4.7 degrees Celsius. That represents an increase in seasonality in the environment of under the Pliocene boundary conditions. Here I'm showing you the seasonal zonally average anomalies with respect to PI and modern, and the key thing to just take away is that there is no real difference in the southern hemisphere. I mean, there's a reduction in amplitude for the modern, but that's just CO2 effect, but the relative shapes of the curves and the relative locations of anomalies are relatively the same. But in the higher latitude in northern hemisphere, you see the blue curve here down here in the modern, which showing that in December, January, February, these latitudes are colder compared to 400 ppm control simulation. And it's also showing that March, April, May is a little bit colder compared to PI as well. So what is really going on? Let me first show you, this is the same figure that I had before, the DJF Pliocene temperature anomaly with respect to 400 ppm modern. But on the left-hand side for comparison, what I'm showing you is the modern day observational temperature trends for the last 2 decades obtained by Sun et al. With the ERA interim data. So this is showing that in the modern day, currently, the continents are cooling, whereas the Arctic is warming. And this pattern has been called the warm Arctic cold continents pattern, and has gotten a lot of attention recently because of the whole thing that climate is warming, so why are we seeing so many cold seasons in northern hemisphere? And a lot of effort has gone into here. Some of these research references are here, and most of these have pointed to the decline in the September, October, November, that is the fall sea ice, which has been related to this pattern. Now, many linking mechanisms have been explored, and there's a lot of discussion amongst investigators as to what is the right response. But one of the primary mechanisms that has been proposed, one of the reasonable mechanisms that has been proposed, is that warming in the Arctic here leads to the greater turbulent exchange of heat energy between the ocean and the atmosphere. And that leads to a destabilization of the atmospheric column, and it increases the temperature in the column, and it decreases the meridional temperature gradient. Now, the thermal wind, which is the jet streams, the thermal, which is defined by the thermal wind relationship, depends on the zonal temperature gradient, and when that decreases, the zonal winds decrease and they shift equatorward. This has been studied in a lot of simulations. Actually, first I will tell you that this is what we observe in our simulations. This is the zonal mean zonal wind anomaly, Pliocene minus modern, for each of the 4 seasons. And while in JJA and SON, there is no significant pattern of shifting of the northern hemisphere jet that is seen, in DJF and MAM, you see this pattern of shifting in the wind, and there's a significant shift. The magnitudes are on the order of 7 meters or so per second. this kind of shifting of jet in response to northern hemisphere near surface warming has been observed in many different simulations and has been studied in detail. For example, here Clara Desser et al. Have used the CCSM4 model, the model that we are using to study the impact of the how the jets respond and how the meridional profile of the atmosphere responds in response to various sea ice reduction scenarios. And they find that the jet moves equatorward, as has been found by Amy Butler et al., who used dry dynamical core to study how the jet streams react in response to near surface Arctic warming. And many other results have found that as well. Now, what is interesting is that these results are sensitivity studies. So what is often done is that you apply some albedo control to your ice sheet, to your ice to melt it or increase it, or you apply some artificial long wave radiation forcing to your ice to melt it or increase it, or you apply some other kind of control in order to get the response that you want, or you simulate your model with an RCP scenario so that you see the melting of the ice sheet being driven by the increased radiative forcing. But what is interesting in our simulation, what I'm showing you here, is that we did not do any of that. Any kind of melting that has happened in the ice, in the sea ice, has happened because of the specific feedback mechanisms that have been active with the Pliomip2 boundary conditions. So when we look at the 400 ppm Pliocene and the 400 ppm modern day, and we look at this thing, there is no anomaly in radiative forcing, and there is no anomaly in terms of any kind of artificial change that we have applied. So this shows that these results that people have been working towards is very robust. It is something that comes up naturally even when you don't directly force the ice or in one way or another. So we think that so this shows that this is a fairly robust response, and I guess I do not have time for sensitivity studies, but I was just going to show what happens when you change the ice sheet and orography. But I guess the main thing to show here is that in all of these simulations, yeah, I know. The DJF, there is a shifting in the jet and a shifting in jet slightly in the MAM month as well. And this happens regardless of whether there is it's an ice sheet sensitivity experiment or an orography sensitivity experiment, because in all of these cases, there is some ice that is sea ice that does decline. More in the orography experiment and less in the ice sheet experiment, but that is the case. So here, this is my concluding remarks. We have simulated 8 Pliomip2 simulations. The new PRISM 4 boundary conditions in Pliomip2 lead to a better warming in higher latitudes and lead to better agreement with proxy-based inferences. The jet streams are seen to move equatorward in response to ice decline in the Pliocene. And this suggests more intrusion of Arctic air into mid-latitudes can become a permanent characteristic of the 21st century, because these observations that I was showing you before, they're only for the last couple of decades. One of the things we want to understand is whether this kind of shifting in the jet pattern can be expected to be a robust and permanent aspect of a future warm climate, or is it just a transient aspect of the climate response? So thank you very much, and I can take your questions.
For this talk, before I ask my question, I need to double check. You say that you have sea warming in the oceans and a cooling on the continents. Is that correct?
Compared to it's an anomaly. It's compared to modern day. If you did not have Pliomip2 boundary conditions, you'd see the modern kind of climate. So compared to that, the changes that have been implemented with the closure of straits and the changes in ice sheet, they lead to that kind of pattern.
My problem with that is that you don't see it in the data.
Which data is that?
All data. All terrestrial data.
Well,
so strong cooling and there's a strong winter warming. Strong warming, sorry, and in particular in the winter.
Wait, well, I can only speak about a model. I mean, I have no idea what the data.
There are quite a few data.
Yeah.
Have a look at it.
But one of the things is that if you look at the global annual average, it is still a warming. You do not, the cooling pattern does not come up because the warming in the other months in JJA overwhelms that, and in the annual average, which I'm pretty sure the proxies will only record the annual average, it doesn't record. Okay, all right.
That's okay. Yeah, I want to especially acknowledge Sina Panitz and Paul Bacham, because most of the data I present here is produced during the course of their PhD thesis. And before I go to sort of the land-ocean interaction and go back to that, very briefly, recap of what Alan said already. The Pliocene, it's a warm world, it's a high CO2 world between present and pre-industrial. No, pre-industrial and present, yeah, basically. It's globally warmer in the oceans, it's globally warmer in the atmosphere. It is a warm world with a strong Arctic amplification is a world where the model and data mismatch is largest in these high northern latitudes. Sea level is higher, and there is larger implications of these gateway changes than what maybe previously had been thought. But as Alan also said, a lot of what we know about the Pliocene and a lot of studies that is done focuses in on the mid-Pliocene warm period, or the time slice. What I will present here is records covering 2 million years, so from 5.1 till 3.1 million years ago. So it's sort of covering a much larger interval than what we focus on. When I say high latitudes, more specifically, I will focus in on the Norwegian Sea in the eastern part of the Nordic seas. It's a part that is bathed by warm Atlantic water, bringing warm, salty Atlantic water from the North Atlantic up along the coast of Norway into the Arctic Ocean, losing its heat gradually as it progresses northwards. In the other part of the Nordic Sea's basin, you have the opposite situation. You have the cold polar water flowing southward from the Arctic Ocean in these Greenland currents. So you set up a dynamic basin with a very strong temperature salinity gradient, both in the north-south and in the east-west direction. If we then go to Norway, the vegetation of today is dominated by boreal forests and alpine tundra if you go up to higher latitudes. But you also have this belt of more deciduous forest in the really most southernmost Norway. So if you then go to the ocean and focus on the alkaline temperature reconstruction that we have, the Pliocene is warm, but I hope you can see that the Pliocene is not consistently warm. The stippled line represents the Holocene mean from the same site, just as an indicator. It sort of oscillates between phases of warmer than present conditions and conditions that are more equal to what we see today. In the warmest phases and in the warmest parts of the warm phases, we have temperatures up to like 6 degrees warmer than during the Holocene. On the top, you have an ice-rafted debris record from the same site. Just to sort of show that these, like during the colder phases, we actually do see this occasional iceberg or piece of ice that manages to hit this site. It's not, don't think about it as like an armada of icebergs coming and getting here. It's sort of like this random guy that decides to go to the tropics and then it kills it. So, varying conditions. I also want you to believe me when I say that the changes that we see is not restricted to the surface of the ocean. We see similar changes and similar sort of large-scale oscillations throughout the water column at this site, both from flora and fauna, oxygen and carbon isotopes, plankton and benthic. So if we then go to land and see what the vegetation does, the pollen records that I show here is all from the same samples that we have done all the marine proxies on. So it's a marine pollen reconstruction. The chronology is the same. It's like directly comparable, linking directly ocean and vegetation. And what I present here is just the relative abundances of the conifers, excluding the pines, Scydophytes, and sphagnum, as a representation of the vegetation changes that we see. And I hope you agree with me that there is some similarities between these records, that also these vegetation records show these oscillations on long term. And also referring to Sina's paper that Alan referred to, 2016, in Climate of the Past, and also her paper that is now in revision with a long record, you sort of have these oscillations between the cold temperate vegetation and the boreal vegetation. And when we have the boreal vegetation, that's basically where you have conditions that are comparable to today. The pollen that we see in those samples compares to the pollen that was found in Holocene samples from the same site. So when we have colder ocean temperatures, we have boreal vegetation and conditions pretty comparable to today, both in the ocean and on land. And in the other times, we have a warmer vegetation and warmer sea surface temperatures, and also sort of a different circulation of the whole water mass. So I would say that it seems like there is a clear link between the oceanographic changes that we see in the Nordic seas and the changes that you see in vegetation over land. And the question then is, of course, why do we see these large-scale changes throughout the Pliocene? And how does it link to the regional signals that we see? As I started out saying, this site is on the northern pathway of the Atlantic current. And so the next then, it's logical to go to the source areas of the warm water masses. So this is from the subtropical Atlantic, same proxy, showing continuously warmer conditions throughout the Pliocene, as far back as it goes. It's going a bit further up north in the Atlantic. It's also consistently warmer throughout, significantly warmer throughout the Pliocene. While, just as a reminder, when you go to the Nordic seas, we see more of these changes, and especially we have some of these intervals with sort of colder conditions. And I really want to focus a bit on this coldest interval before the 4 millions for the rest of the talk. The timescales of the changes that we see indicates that tectonics is a potential factor in this. Alan also said that there have been several studies looking at the effects of these gateway changes, or gateway differences that existed during the Pliocene, primarily to try to sort of get the data model mismatch to minimize. And the problem there is that the data shows warmer conditions than the model does. So basically, this is sort of, all of these experiments have been done to explain changes that goes in the opposite direction of what we want to try to explain here. But if you look at the locations of these sites that I've been sort of presenting here, the one sort of primary suspect, in a way, for me at least, as a factor that that separates the North Atlantic from the Nordic seas is the Greenland-Scotland ridge, crossing over between Greenland and Scotland, sort of over here. And it is one of these gateways that has changed or was different during the Pliocene. The problem is that the Greenland-Scotland ridge was basically deeper than today throughout the Pliocene, and several studies have been done looking at the effects of this. Marcy Robinson has one, Dan Hill has one, and they all show that you do get a warming in the Nordic seas by a couple of degrees. And that's sort of what we see also for the general long-term trends, if you forget about these sort of strange intervals that we have. But when you look at these records of the residual depths of the Greenland-Scotland ridge, I'm sort of very curious about these sort of minor disturbances, can you say that, in the record, that yes, it's deeper throughout the Pliocene, but there seems to be some sort of indications of minor activity around between 4.5, 4, but it's very uncertain, the timing. These records are presented on their original timescales. The PMAG is outdated, so it should be updated in that sense. Also, the Poradal data has been adjusted to fit with the Denmark Strait overflow waters because they've been looking at the component of northern waters, while the area we are interested in is in the other side of the basin, in the Ferro-Shetland Channel, in the inflow area. So there's a lot of things that would have to be, to actually use this, the indications that maybe there are changes in the Greenland-Scotland ridge that can influence the area. This has to be looked further into. But I find it tempting to sort of like speculate that maybe these minor changes has an impact in addition to other tectonic changes that goes on through the Pliocene. And so it does maybe speculate that there is a threshold somewhere in terms of setting the conditions of the oceanography of Nordic seas, and thereby also setting the vegetation changes over land. So basically, summarizing quite quickly, we have a 2 million year long record with paired ocean and vegetation data. And as I said, I always show you here some selected records from the core. We have these phases of warmer than present conditions interfering with phases of conditions pretty similar to what we have during the present or the Holocene. And the corresponding changes between the ocean and the vegetation sort of indicates that we have a very strong link between what's going on in the Nordic seas and in the ocean, but also then how that reflects into the vegetation changes on land. And since the oceanographic changes that we see in the Nordic seas is so different from what we see in the North Atlantic, this is probably also quite locally linked to the Nordic seas. And I also then say, as I speculate, that maybe this interval, the cold interval before 4 million, could be somehow linked to minor disturbances in the Greenland-Scotland Ridge. And I'll leave it there by just showing you this beautiful data once more, and take questions if you have them.
Have you looked at the insulation forcing around 4 million years? It looks around this time period is different.
It's the obliquity is sort of low amplitude during this interval. And it's also just at 4 million before you go up, you have in one of those the low sort of modules of the long-term eccentricity forcing. So these things do happen at that site. And in addition, it's also the change, like the strong warming at 4 million, it might also be linked to the Bering Strait and changes in that area, setting up extreme contrasts between the eastern and western part of the Nordic seas.
Okay, thank you.
So there's a lot of things going on.
So today I'll be presenting a terrestrial Pliocene temperature record based on biomarkers for the whole region of northwestern Europe. And I've been doing this with my supervisors, Jaap Damste and Francine Petersen, and my collaborators, Dirk Munsterman and Tim Adondes. So we do know quite a lot about Pliocene sea surface temperature. So these are the PRISM-3 sea surface temperature records. You can see that they're really nicely globally distributed. And yeah, most of them are pretty nice confidence as well. However, with terrestrial temperatures, we have a bit of a less of a sort of nice story. So this is due to the fact that we have relatively few proxies that we can use. So we can't really do intercomparison sort of studies. And yeah, relatively scarcity of terrestrial archives. So there's really sort of few nice terrestrial temperature records that we have for the Pliocene. It's also kind of really important to have terrestrial temperature records for the Pliocene so that we can actually say something about the hydroclimate and within comparison to sea surface temperature records, for example. So with that, I'd like to introduce you to this new biomarker-based continental paleothermometer. It's based on that molecule you can see there, and it's called a glycerol dialkyl glycerol tetraether, which is why we call them GGDTs for short, because it's quite a mouthful. So these are membrane-spanning lipids, and they're produced by bacteria in soils worldwide. So you can see that the bacteria actually make them as a lipid monolayer, and upon cell death, then these biomarkers are actually extremely, extremely stable, and you can find them in marine sediments up to 140 million years old. So as I said, they can be used as a continental paleothermometer. This was discovered first about 10 years ago by Johan Weyers in Utrecht, and he looked at 239 globally distributed soils and looked at the distribution of the 9 most abundant branch GGDTs in those soils. Now, they found 2 very nice relationships. One of the relationships is with the number of the cyclopentane rings with soil pH, and the other relationship is with the number of methyl groups with temperature. So we think this is because the bacteria introduce more methyl groups at lower temperatures to keep the membrane fluidity, so to stop the actual bacteria from freezing. So as I said, they're actually produced mostly in the soils. And then what's really great for paleoclimatologists like us is the fact that they're transported to the marine sediments via rivers, runoff, and precipitation, etc. So in effect, you can actually take a core close to a river mouth that has a high influx of terrestrial material and actually analyze those branch GGDTs and say something about the terrestrial temperature evolution of the whole catchment. So this is in effect what we've done right here. We took a core from the Dutch Geological Survey. It's drilled sort of close in this Rhine-Meuse Scheldt Delta area. During the Pliocene, this river system would have also started as well, so we expect that there would have been a lot of terrestrial material at this site. It's called the Honk core because it's drilled in this tiny town called Honk, close to Rotterdam. And there I've actually shaded in blue the approximate Pliocene paleo coastline, so that we can see that during the Pliocene, this area was a sort of coastal marine site, and obviously during the Pleistocene, we expect that the sea level obviously decreases and the site will become more terrestrial. Also, preliminary pollen studies and investigations into this Pliocene deltaic wetland have found that it's actually quite similar to the Florida Everglades today. And what's actually really cool is the fact that crocodiles and alligators also died out in Europe around the Pliocene, so perhaps there were a few crocodiles there as well. So without any further ado, here's a temperature record that we generated. If you notice, I haven't put any exact ages on the bottom. This is because the age model right now is actually just based on biostratigraphy, so first occurrence dates and last occurrence dates of dinoflagellate cysts. And we know just from that age model and the preliminary one that it actually goes from about 5 million years ago to 2.4 million years ago. However, I'm not going to interpret this record because 2 years ago, they actually found that branched GGDTs could be produced in aquatic environments. So either the river, either a marine water column, or either marine sediment. So it would be useless to interpret this record because we know that branched GGDTs can be produced in aquatic environments, and obviously this record might actually be a mix of a terrestrial and an aquatic signal. So we do need to correct for that. So if we look further into detail into the branched GGDT distribution of the sediments that we have, the Pliocene sediments, we can compare them to the modern soil branched GGDT distribution. So this figure, don't pay too much attention to the axes. It's just a nice ternary plot that we see, that we plot to see like a nice shape. So those black dots are the modern day soil samples, and you can see that they make some kind of nice shape, except for that one outlier there. So if we plot over the Hank core branched GGDT Pliocene samples, then we can see that they sort of plot close by to these soil samples. So they don't actually plot right on them, which kind of is a little bit worrying, but they do plot close enough. In particular, if we actually plot two marine sediment samples where we know that branched GGDT production has been occurring, then we actually see some startling differences. So Jaap published a paper last year where he looked at sediments from the Birel Delta in Indonesia and from Svalbard. And he found, well, he knew that he sort of used the number of rings in these branched GGDTs to say that there was in situ production. And you can see that these two sites actually plot very, very far away from the soil samples. So we can say that the Hank site is indeed a mixed contribution site. So as I said, Jaap looked at the number of rings in particular in these two marine sediment sites, and he came up with an index, which is the number of rings of the branched GGDTs as an indicator for in situ branched GGDT production. And this sort of ties into what I was saying before about the pH control on them, because we know that marine sediments have a very, very high pH compared to soils. Therefore, any branched GGDTs produced in that environment will indeed have a lot of number of rings. So using the number of rings as an indicator for the in situ production, we came up with a method to correct our record. So we took, I just switched the axes there, so we took the number of rings and calculated that index for all the Hank sediments, and we made a record out of that. So you can see that during the Pliocene, we have like a high number of rings, and during the Pleistocene, we have a low number of rings. So this really ties into the fact that it's an indicator for in situ production. So we went through a few steps. We did end member modeling, and then we sort of translated that number of rings to a percent aquatic, percent terrestrial record. So obviously, during the Pliocene, we have a little bit of aquatic input there, and during the Pleistocene, we have actually hardly any. So if we go through a few more correction steps, which you can ask me later on, we come up with a corrected record for the Hank site. In gray there behind, you can see the uncorrected record. So you can see that the corrected record actually has a higher amplitude of temperature variation, but the Pleistocene part remains basically the same because we have no correction for that interval. What's really nice is the fact that these temperatures that you can see for the early Pliocene, so I've highlighted that they're actually matched with some other temperatures that we have for Europe during that time. So if we look at these temperatures we have from the Netherlands, we can see it's about 13 to 14 degrees. And from an earlier study by Donders et al., using the same method, they found a temperature of 14 degrees for Germany. And using another method, seeds, fruits, and leaves, Mosbrugger et al. Found temperatures for Central Europe of 13 degrees. So it seems that indeed this proxy seems to be in agreement with the other ones insofar as it goes so far. So if we try to interpret this record, I've just put two other records on top. I'll just introduce them first and then I'll go through the whole temperature record. So this record in the middle is the BIT index, and that is a relative indicator of terrestrial matter input. So you can think of it as a kind of how much concentration of branch GGTs are coming into the core. So you can see that during the Pliocene it was marine, so there's hardly, there's few. And during the Pleistocene, it actually just swings right to the other way. So we have a really, really nice Pleistocene transition in this core. And then the same thing for the delta 13C of organic matter. There's a very nice decrease of that throughout the record. So using the preliminary age model, we can try to assign some of these intervals in the Pliocene. So I've just highlighted 3 there. Let's talk about the M2 first, because that's what immediately stands out. So we have this M2 part here, which has a lower temperature than the current matter of the Netherlands. And it also is correlated with an increase in the bit index and a depletion in delta 13C of organic matter. Same thing exactly for this earlier Pliocene bit. So we see a decrease in temperature and an increase in terrestrial matter. So it does indeed seem like these intervals can be interpreted as glacials. And obviously after the M2 event, then we have this mid-Piacenzian warm period, which is characterized by quite nice stable temperatures in this record. So my collaborators looked at the palynology of the record. So my collaborator at the Dutch Geological Survey looked at the dinoflagellate cysts. So he made a record of the cold species and the warm species, and then he took out a sort of non-diagnostic species. And then Timmer Donders at Utrecht also looked at the pollen. So here is the main pollen trace, and here is a trace of the Osmunda spore pollen that they actually had to take out of the pollen diagram because it would have drowned everything else out. So if I highlight the 2 periods that we looked at in the previous slide, then you can see that the periods of decreased temperature indeed are nicely correlated with the higher abundance of cold dinoflagellate cysts, for example, Habiba-cysta tectata. And then you see during the mid-Pliocene warm period that you have an increase in warm species there, which is quite nice. Also, what's quite startling is this Osmunda spike here, which occurs exactly at the point of this, what we think is the M2 glacial or some kind of glacial or combinations thereof. And what was communicated to me by Timmer was that this spike could actually indicate a relative sea level drawdown actually exposing the shelf. So to conclude, I'd like to say that the number of rings of the branch GGTs can be used to extract a terrestrial temperature signal from a marine core. So all is not lost with this proxy. And the resulting record is in great agreement with palynology and bulk organic carbon properties. And northwestern Europe was indeed warmer than present during the early to mid-Pliocene by about 2 to 3 degrees. And what's really great about this record is that it shows the influence of the early Pliocene glacials actually extended into northwestern Europe. So I'd like to thank everybody that helped me, and thank you for your attention.
So the calibration for the branch GGTs you're using is based on terrestrial soils?
Yeah.
But you've applied it as well to these sequences for the Pliocene, which are marine?
Yeah, so that's the start of the proxy, basically. So the calibration is based on terrestrial soils. However, we apply it to paleo sequences but now we have to keep in mind with our corrections. So before, people just applied it to the sort of marine sediments, but now, you know, I've shown that you need to actually correct it. Yeah.
But so the terrestrial soils calibration has been applied to marine production of the branch DGTs. So it's a marine signal that is converted into a temperature using a soil signal, soil calibration.
So no, so for the branch GGDTs that I extracted from the core, through my correction steps, which I didn't show here and will be published in a paper soon, I actually managed to subtract the aquatic signal. So you're left with just a branch GGDT distribution, which should reflect only soils, and therefore then you can apply the soil calibration.
Okay, thank you.
Yeah, so I wasn't clear enough in the presentation.
Very interesting that the temperature curve seems to match the pollen spectrum. But what I do not understand is I missed the typical pattern of the Pliocene transition. You don't see a cooling there. So it seems that the Pliocene, the Pleistocene, is even warmer.
Yeah, so you see...
If you put it together with the pollen.
Yeah.
The next one, yeah.
Yeah, this one, yeah. Well, the general pollen diversity seems to go up, so maybe there is some sort of change there. But yeah, it goes from typically, obviously, conifer dominated to a bit more. But yeah, it's not...
It'll be interesting to see the age model then at the end.
Yeah, it's coming out soon. There'll be Delta 18O work done on the early Pliocene bit, so to tie it with the LRO4.
Today I'm going to talk about my work in the project Cynamo, which aims to reconstruct Mediterranean overflow water fluctuations at orbital scale during the Plio-Pleistocene transition and the climatic variations in the Iberian margin for the same time interval. And for this, I'm using this site, EU1391, which was collected during Expedition 339, IODP Expedition 339. And this site is located in the path of the Mediterranean overflow water. And it presents an almost continuous sedimentary sequence from the late Pliocene to the present. Why this time interval? Well, because during this interval we have the intensification of the northern hemisphere glaciations, and also because some studies suggested that because of the late Pliocene aridification in the Mediterranean region, we can have an intensification in the Mediterranean overflow water. So we wanted to test this hypothesis in the MO path. And for those of you who don't know, the Mediterranean overflow water is a warm and high salinity intermediate water mass, and it goes out from the Strait of Gibraltar, and it's a strong contour current which flows along the Iberian margin, and at a water depth between 700 and 1500 meters. And this current is very important because the Mediterranean overflow water, the MO, is an important salt contributing member to the North Atlantic deep water and to the thermohaline circulation. The H model for this interval is still in progress, but basically we are correlating our Cibicidoides pachyderma, which is a benthic foraminifer, well, the delta O18 from this species with the Lysikian Raymond record. And so far, we still don't have the resolution we would like to have, but we have a fairly robust H model. And we also use the paleomagnetic data. Unfortunately, we have 3 no recovery intervals from the drilling. And the transition from Gauss to Matsuyama falls within one of these no recovery intervals. But we know this part is the Pliocene and this part is the Pleistocene. And also to tie our benthic delta O18 record with the Lysikian Raymond record, we used 2 biostratigraphic events from benthic foraminifers. These are not the events from the seaboard data. We refined those events. And those events are the last occurrence of Globorotalia punticulata and the last occurrence of Sphaeroidenelopsis seminolina. And well, we analyze XRF in our sediments, and this is the calcium-titanium record. Calcium-titanium normally indicates warm temperatures when you have more calcium, and colder temperatures when you have less calcium. And in this record, we can clearly see that during the early Pleistocene, we have changes, variations between glacials and interglacials, very well correlated with the delta 18. However, during the Pliocene, the pattern is not very clear, is not correlated with the delta 18, and it looks like there is higher variability. So far I don't know how to explain this very well, but there is clearly a different pattern. And when we look at our carbon-14 record from the same benthic foraminifer, we can see that there is a change between lower values and higher values during the early Pleistocene. And in present-day sediments, this is data from one of my colleagues, Emilia Salgueiro, and she did a study in this region. And we can see that the MO values for the carbon-13 are higher than the North Atlantic deep water values. So we think that during the Pliocene, maybe the site was more influenced by the North Atlantic deep waters, or a mixture between both the Mediterranean overflow water and the North Atlantic deep water. Whereas during the early Pleistocene, the Mediterranean overflow water got intensified or deeper, and then the site is more affected by the MO. So maybe this is why we start to have a clear signal between glacials and interglacials here, and here the signal is not that clear, I don't know. And we have also done grain size analysis, and here we have the clay record. This is the silt, and this is the sand. And well, most of the sediment is composed of silt, and we can see an increase in the silt during the early Pleistocene. So we think the Mediterranean overflow water got intensified, or as I said before, maybe it got deeper, the MO. So in this site in 1391, we are seeing here the changes between glacial and interglacials. But here we don't really see changes between glacials and interglacials. Another interesting thing is that during the early Pleistocene, the silt record is very well correlated with the calcium-titanium. So every time we have low calcium during glacial periods, we have high silt, which means the MO got intensified, and the other way around, of course. But when we look at the zirconium-aluminum ratio, which has been used during the late Pleistocene to track the strength of the MO, we see a totally different pattern. So our silt is not, it doesn't have the same patterns as the zirconium aluminum. And it looks like the zirconium aluminum variability has a higher frequency than the silt. And I did this experiment to, so I compared, instead of just comparing the total silt with the zirconium aluminum, I compared the zirconium aluminum ratio with all the fractions in the silt and also the sand. And the thing is, the maximum correlation is with the very coarse silt. So the patterns of the zirconium aluminum are very similar to the very coarse silt. And those, all the peaks in the very coarse silt and in the zirconium aluminum are not really dependent of glacials or interglacials. They occur in both. So what we think is that the zirconium aluminum is showing a different signal, and this is a preliminary age model I did just for the early Pleistocene. And what we can see here is the insolation, the summer insolation, for the same latitude as the site. And more or less, the peaks in the zirconium aluminum curve are related to minimums in the summer insolation. So we think the zirconium aluminum curve is related to precession. And the idea right now, this is work in progress, is that whenever we have high insolation, we have more rain, and then we have more clays going into the basin, so we have less zirconium. And then when we have low insolation, we have less clays going into the basin and more zirconium. So maybe the zirconium aluminum in this site is indicating the input of sediment to the basin rather than the strength of the current. And so in conclusion, our carbon-14 and silt records suggest an intensification of the Mediterranean overflow water or deepening during the Pleistocene transition. And therefore, we start to see clear glacial-interglacial variability at this site, whereas before it looks like the variability we see, maybe it's more precessional. And so during the late Pliocene, we see a different pattern, and deep water conditions were probably different, maybe because the site was in the interface between the North Atlantic deep water and the Mediterranean overflow water. And the zirconium aluminum ratio in this site is linked to the very coarse silt fraction, and is probably related to a precessional forcing, which maybe drives the sedimentation input in the basin. But well, if you have any suggestion, I can take it. Thank you very much, and I also would like to thank all my sponsors.
Did you have the benthic oxygen isotopes as well as the carbon? Like, do you see any change in the temperature or properties of the water mass that's bathing the site?
I haven't done the magnesium calcium for the temperature of the water mass.
Do you see any change in the oxygen isotopes?
In the oxygen isotopes?
Did you do? Yeah.
Not really. There is no clear change in the oxygen isotopes. Like, I mean, here there is more glacial-interglacial variability, but it's really following the Lisicki rainbow. There is no significant change like we see in the carbon isotopes. We were also expecting a change because we see this change in the carbon isotopes, yeah. But the oxygen isotopes, maybe the sign is more muted, I don't know.
This talk was supposed to be given by my junior colleagues because it's actually a conference for youngsters, but he was not able to attend this conference. That's why I will present this talk. And you can notice that actually the title of our presentation almost coincides with the title of the session. And basically I'm going to answer the question whether there were glacial-interglacial variations during Pleistocene. Oh, sorry, Pliocene. And this is how it works? Okay. Okay. And it's easy to understand why I made this mistake, because actually I'm a quaternary person, and most of my work was related to simulation, everything what is to the right of this yellow rectangle, but especially for this session we extend our work and simulated also what we call late Pleistocene, because after correction of quaternary, that's more appropriate title. And this is like a byproduct of a long-term project on simulating the all last glacial cycle using Milankovitch forcing only. And we are almost through, but it's already 20 years, so to say, on the way, and we still continue this project. But before I will discuss our simulations of late Pliocene one period, I just will illustrate actually our approach based on entire quaternary simulation. So, of course, we believe that the main force for quaternary climate variability is orbital variations. That's actually the only things which we know precisely about the past, but also about the future, because unlike geoscience, astronomy is precise science. But we know also it's not enough to explain these regime changes like mid-Pleistocene transition, also Pleistocene transition, so we need to add something else. And well, there is a small advantage to be one of the last speakers, because some things were already explained. And you see here this prism for reconstruction. So it was realized now that continents were slightly different than in present. So Alan already explained what is different. In particular, this is, of course, the fact that Canadian archipelago was basically, so to say, filled with the land. Also, the no Labrador, changes in Baltic Seas. And in a few minutes, I will show that actually our model doesn't like this reconstruction. Nonetheless, we use it. So, of course, it's not the only difference between Pliocene and present world. At present, large fraction of northern continents are free of sediments. So this is like a binary map of the world, where blue means very thin terrestrial sediments layers, and blue means thick sediment layers. Of course, marine sediments are separate issue. And so this is what we can derive now from geological maps. And this is what we believe was during Pliocene, because there is no reason why northern continents were not covered by sediments at that time. And in between, so the main mechanism that is believed to be glacial erosion, which gradually removed sediments from the continent into the ocean or to the south. And of course, another important factor is atmospheric CO2, which is believed that it was higher during a late Pliocene, but of course, this is not very encouraging compilation of different reconstructions, which are showing that CO2 during late Pliocene could be any. Fortunately, we don't need these reconstructions anymore, because our model can simulate CO2 of its own. And so this is a very simplistic scheme of our model, just especially for 12 minutes presentation. So the model is called Climber2. Of course, we are developing this model for the last 20 years. And now it has all essentially components. So it's climate, ice sheet, and carbon cycle. And now CO2 is not only computed, but also really used to drive climate. You see here 1.3. Actually, we enhance carbon dioxide radiative forcing by 30%, because our model still does not account for methane and N2O. And we take into account the fact that basically they're following the same path as CO2. And okay, so we have actually three forcings. One is the real one. It's orbital forcing, which, as I said already, we know accurately. But we need also volcanic outgassing, which is on the longer time scale really important. And this sediment mask and topography. And this I would not name forcing. It's like a boundary condition. The only forcing is orbital forcing. And with that, we can, so to say, we now combine this real orbital forcing. We prescribe a certain reasonable scenario for gradual evolution of sediment mass from like Pliocene to present day. So it's a bit of fantasy, of course, here. And as far as volcanic outgassing is concerned, of course, it's absolutely unknown, even what its value is now. But we solved sort of inverse problem, and we found that model require 20% higher volcanic outgassing at the beginning of quaternary, or actually at the end of Pliocene, as compared to present. This not necessarily should be volcanic outgassing. The same 20% could be from increase of sediment in the silicate weathering, so or combination of these two. But because we have no idea about changes in silicate rocks over this period of time, we just play here with the volcanic outgassing. Okay, this is input of the model, and now we see output. So basically, that's simulation for the last 3.5 million years with a fully interactive Earth system model. And actually, you can notice here that actually there's not a single line, but a family of line. Actually, this is a large ensemble of simulation with a total length about 50 million years. So it's definitely the longest ever simulations with geographically explicit models. And I hope that we produce less carbon dioxide as the second speaker. So now I will move, of course, to the subject of this presentation. So it's late Pliocene. I cannot discuss the rest. I had a poster today on another session, so those who had time to attend it, you can know more. But otherwise, you must to believe me that the model successfully simulate glacial cycles over quaternary. Now I'm moving to the late Pliocene. yeah, and of course it's not only change of the subject, but also change of direction of the time axis, so the direction is the right one, from left to the right. And what you see here is simulation. So blue lines, it's empirical reconstructions, of course, for benzene delta NTO, CO2, sea level, and black line is empirical reconstruction for delta 18O, and blue are model simulations, because of course we don't have reliable reconstructions for this period of time. So blue lines are simulation for present day geography. So we started not from prism for reconstruction, from present day geography. So you can see here there's some agreement and certain disagreement, and particularly model doesn't want to simulate M2 events, so it's for reasons which we are still trying to understand. Or I mean, in fact, orbital force is not as a reason for that, so it should be something else. It's already useful to learn. But and what we see here is that we still have some glacial cycles, so we have sea level variations of at least about 20 meters, sometimes less. CO2 variations of about 20 ppm, and the global temperature is also changing by about 1 degree. So, and if we apply prism for reconstruction, this is green line now, so you see a problem. So actually models start to simulate relatively long glacial cycles, quite pronounced, of course, with large variations. That's more look like as a early Pleistocene glacial cycles, probably too much. And interestingly, if you will make a spectrum analysis of this simulated delta 18O power simulations and compare it with Lisicka-Raymer spectra. So for present day aerography, model correctly simulate maximum at 40 kiloyears world, so it's still 40 kiloyears world. Of course, we have probably simulate too much precision, but interestingly, there is another peak about 60,000 years in data which we don't have in the model. However, if you use a prism reconstruction, then actually model simulates 60,000 years world, and not a 40 kiloyears world, and actually precision is substantially reduced. So it's definitely the land mass, or so to say. Aerography is a matter here. The model is very sensitive to that. Probably we have to change other parameters or slightly reduce elevation of this prism for reconstructions, because as I said, model definitely doesn't like that it's too much land and it's too high. Okay, so you can compare that maximum ice extent and thickness during late Pliocene. So it's with prism 4 and with modern geography. Of course, with modern geography, we have a thinner ice sheet and smaller, because all these straits and streams allow, so to say, to evacuate ice and prevent a growing as large ice sheet as here. So definitely, this look like more like a quaternary ice sheets, while this probably would be, so to say, maximum extent of ice sheet during Pliocene. And okay, this result is actually not really new, because we published something like that already 4 years ago in a slightly different model configuration. Just for simplicity, I will concentrate only on 2 right panels. Actually, what is shown here is a simulated anomaly of zonal mean temperature. Upper panel is annual temperature, SST, sorry, it's not land temperature on the left. On the right, it is SST. So annual, and then the bottom, it is summer temperatures. Red show average over entire late Pliocene, so late Pliocene, yeah, so about 500,000 years, sorry. And reddish colors represent entire range of variability related to glacial cycles and orbital variations, and while blue is prism reconstructions, that's prism 3, I suppose. And as you can see, actually variability on orbital time scale actually much larger than average signal, and actually as we expected, the prism reconstruction is close to the maximum, so to say, temperature changes, so definitely warm biased if model simulations are correct. Basically the same you can see for land summer temperatures, where variations are much larger again than the average signal. Okay, so with that I already arrived to conclusion. So first of all, our model simulation shows that although Pliocene is much more stable and less variable than quaternary, but still have substantial variations on orbital time scale, order of 20 ppm for CO2, 20 meters for sea level, and about 1 in global temperature. And as far as the regional and seasonal effects of orbital force are concerned, so this effect is comparable or even much stronger in some cases the global mean response, which of course has important implications for the data model comparison. Yeah. Thank you for your attention.
I wasn't quite clear when you switched to using the Prism 4 paleogeography. How did you deal with then the transition between the Prism 4 paleogeography and then a more sort of standard modern paleogeography as you move closer towards the present?
For entire quaternary, we still didn't solve this problem, so we just use modern geography, while for specifically for this late Pliocene simulation, we simply perform 2 experiments. We're not trying to switch from one to another. Simply one experiment, like in blue, was continuously present day orography, but of course sediment mask with complete regolith. Okay, probably this was your question. And the second experiment, the same regolith, but Prism 4 orography.
Okay, thanks.
One of the major glaciation in that late Pliocene is the M2. And you said, okay, it's true that it's not climate, very quickly. So could you say a bit more about that?
No, I didn't say it is not climate. I didn't say, I said that it is not Milankovitch. So it should be something else. For example, for whatever reasons, reduction of volcanic outgassing, I don't know, asteroid collision, whatever else. So not direct, I mean, simply with orbital forcing, there is nothing special. We cannot simulate this big excursion. So I'm not saying it is not real. It is real, of course. We can't simulate it so far.
Thanks.
Just a quick comeback on the M2. I mean, I know that there are ongoing discussions within the paleoceanographic community about the benthic isotope stack and whether or not there's some missing segments in there. So actually the M2, if that's true, and the new updated Lazeki-Ramo stack turns out how some of us think it might, it might mean that actually M2 is associated with some pretty significant orbital change because it moves out in time. So that might also explain some of your phasing problem that you have.
Yeah, if so, then of course it will be, we can reconsider.
Yeah, welcome everyone to my talk about the mid-Persengian and the Asian interior. And what you can see already from these 2 pictures is that I will take you to a very dry area today. And the climate in the Asian interior is mainly controlled by the East Asian monsoon and the westerlies. And the East Asian summer monsoon provides warm and wet air directed north and westwards during summer months, whereas the East Asian winter monsoon provides some cold and dry air in winter months in the opposite direction. Now, the Indian summer monsoon does not have just have a very limited effect on our study area because of the high topography of the Tibetan Plateau and the rain shadow effects. The westerlies, on the other hand, provide some moisture sources from the Atlantic and the Mediterranean to the study area. And so the question is that, what already sediment records have shown is, for the East Asian winter monsoon, we have strong evidence that there was already a strengthening during this time period, but for the East Asian summer monsoon, it's a bit controversial and it's still subject of discussion. So our question is, how variable was the climate in the Asian interior during the mid-Pliocene warm period? And was there warming? We saw that there's warming in high latitude areas, and now we want to have a look at this mid-latitude study area. And if so, if it was warmer, do we see a wetting or a drying in that area compared to today? And if we see any seasonality changes in that period during the Mid-Pliocene warm period, and what possible forcings are there for the climate changes? So in terms of study sites, we chose 3 study sites in the Sidon Basin, so the SG1B core, the Maha section, and the Kunlun Pass Basin. I already have to exclude the Maha section because I had a look at the pollen samples and they do not show any pollen preserved in there. But that's still okay because the SG1B core and the Kunlun Pass Basin, they show a strong contrast in both like topography. They are like 2,000 meter different nowadays, and also in terms of precipitation, because the Kunlun Pass Basin is still under the effect of the East Asian summer monsoon, whereas the dominant precipitation source for the northwest of the Sidon Basin is considered to be influenced by the westerlies. So for the H model of our 2 records, the SG1B core there was magnetostratigraphy conducted on the core, and you can see just some images of that core, and it has a really good relationship to the with the reversals. For the Kunlun-Pass basins, the record that I will show, there was already done some lithostratigraphy, which has correlated to a different outcrop samples in the study area where magnetostratigraphy has been conducted, but our project partners want to go back next summer for field trip season and have more constraints on the H model, so this is just preliminary. All right, before we go into what the vegetation looked like in the mid-Persendian, just to remind you, we're in a really dry area with deserts and semi-deserts, and we have some shrub vegetation in there, so it's really dry. And so what the pollen diagram shows for the record in the Sidon Basin, the diagram is grouped basically into coniferous trees, broadleaf trees, herbs and shrubs, and it goes from 3.34 to 3.1 million years. You can see that the diagram is dominated by xerophytic taxa, especially Chanopodiaceae, Artemisia, Ephedra, and Itraria, whereas we just have a very low or low concentrations of coniferous and broadleaf tree pollen, which might come from surrounding mountainous areas and long-distance transport. However, we can see that there's one time interval between 3.17 and 3.15 million years where we have a strong increase in coniferous trees, suggesting that we have a wetter phase during this time interval. For the preliminary results of the Kunlun-Pass basin, we see that, first of all, I should mention that the age is a bit different. The record is from 3.24 to 3.06 million years, but the diagram is organized in the same way as the previous one. We see as well that we have a dominating composition of Chanopodiaceae and Artemisia, so the xerophytic shrubs in the Kunlun-Pass basin, and that we also have low amounts or very low amounts in pollen grains found from coniferous trees and broadleaf trees, except for a minor increase during the time interval between 3.13 and 3.08 million years. So how do we transport our pollen signal for the mid-Persendian now into climate estimates in terms of precipitation or temperature? And here I'm using a study from Wen et al., who was looking at pollen climate transfer functions in temperate Eastern Asia. And he was looking at various modern pollen surfaces combined with meteorologic data such as precipitation, temperature, winter temperature, summer temperature, to determine a relationship between the pollen and our climate parameters. Now, our samples are a bit more to the west located around here, so there might be very tiny bias to the west, to the east, sorry. The transfer functions usually are used for Holocene or Quaternary records, but because we have a quite similar floristic composition on the Tibetan Plateau nowadays and in the Pliocene, we try to use this approach to our both records. What we see for the Sidon Basin is that the precipitation is a lot higher than it is during modern times, and that it fluctuates over the whole record, and especially we see two peaks. This peak is derived from the coniferous trees that I was mentioning earlier during the time interval from 3.17 to 3.15 million years, and we have a second big peak which is around the KM53 event, but is slightly less so. In terms of temperature, the mean annual temperature is almost the same as it is today, but we see that all the transfer functions show that we have colder winter temperatures and slightly warmer summer temperatures in the Sidon Basin. Note that for also this figure and the next one for the Kunlun-Pass Basin, the winter temperature is fluctuating much more compared to the summer temperature, which is almost constant in the record. For the Kunlun Pass Basin, we see a different pattern. The Kunlun Pass Basin, the mean annual precipitation is within like the order of magnitude for what it is today, but we have a different pattern for the temperature record. So we see higher temperatures during the mid-Piocendian compared to today, which is around 3 to 4 degrees. And we see the same trends that we have warmer summer temperatures and colder winter temperatures. To identify possible orbital forcings for our targeted mid-Piocendian, had a look at the spectral analysis of the Artemisia-Cheney-Podiaceae ratio, which is a qualitative indicator of precipitation. You saw these were the two xerophytic shrubs, taxa, that had the highest abundance in the pollen records. And they show that we see obliquity cycles throughout our record and possibly eccentricity cycles, but the problem is that our record is just 250,000 years so far, and that's why we cannot really say if we have eccentricity cycles in there or not. To summarize and conclude, in this figure you can see the mean annual precipitation and the temperatures for like the coldest month for both the Sidon Basin and the Kunlun Pass, and additionally the Artemisia-Cheney-Podiaceae ratio that I was just talking of about, on which we constructed the spectral analysis. And these records are compared to the benthic oxygen isotope stack from Zakros and the Northern Hemisphere insolation at 65 degrees north. And what's apparent is that in times where we have high benthic oxygen isotopes, we see cold and drier conditions in the Sidon Basin, and slightly so in the Kunlun Pass Basin. These are still preliminary. And during times where we see low values in the benthic oxygen isotopes, we really have warmer and wetter phases in our study areas. Now, this is not for all of the events. For example, for the M2 event, we see an initial cooling or like an initial decrease in the Artemisia-Cheney-Podiaceae ratio, but we don't really see changes in the precipitation and only minor changes in the temperature record. So in general, we saw that the vegetation, precipitation, and temperature changes in the northwest of China follow obliquity and possibly eccentricity cycles, and that the seasonality changes of the constant summer temperatures, or we have seasonality changes, whereas the summer temperatures remain almost constant in our records, dependent on the transfer functions. We have there against winter temperatures that fluctuate much more and seem to be colder. And in the Sidon Basin, we saw that we have significantly higher mean annual precipitation, which might suggest that we have a strengthening of the westerlies. Now, in both of our records, we have lower winter temperatures, which might indicate that we have a strengthening of the East Asian winter monsoon, which has been indicated previously by other authors. But the strengthening of the westerlies and the relations to the East Asian summer and winter monsoon are still ongoing working hypothesis, and we have to look more into detail, high resolution of the Kunlun Pass Basin, and also independent proxies such as isotopes, and this will be done in the future. Thank you.
Could you show us the age model? This was
for the Kunlun Pass. I don't. It's
both.
Not done that for the. So there's the magnetostratigraphy that has been constructed on the SG1B.
Okay, but this, you're looking at the section there, presumably, yes?
Mm-hmm.
Which is the section that you're covering? Because I can't read it, even though I'm in the first row.
These are the reversals for the Kona mammoth. I'm not sure if it's possible to make it any bigger, but if you want.
So you're using the reversals, and then, I mean.
And then we're calculating the average sedimentation rates for the core, and then thereby determining the sample depth and age.
Okay, but is there any tuning on, to the benthic isotope stack?
No.
No. Okay.
What kind of sediment is that? Is it lake sediment? Is it mixed?
Yeah, it's
is it
well.
what kind of mud or sand?
Sorry. No, it was a paleo lake, and usually we see mudstones in there, but there are also layers that are rich in halides, so like salt layers in there and gypsum.
Maybe this is above your pay grade, but do you want to comment on the way that vegetation record relates to the ambitions, the current ambitions of the PRISM project and 3.205 interglacial, especially with regard to the fact that, to my eye, the most distinctive anomalies in your records are not at 3.205, but 1 or 2 interglacials later?
Well, for the 3.205, there's this sample that we counted at the 3.207, and this we don't have a sample for 3.205 right now, but this sample already shows that suddenly we also like have a peak in sphagnum there, so we think that there's also like a really wet phase, and from the transfer functions we can also see that this peak here is around the 3.205. Might be good to have an additional sample, or like have it like in a bit more high resolution around the 3.205, but also like this sample indicates that we already have a wetting around that time interval.
Yeah, you do, but the pine is obviously much more prominent in the next interglacial.
Yeah, but what you also need to know is for this peak here, sphagnum has not been part of the transfer function that has been developed by Wen et al. So that's why maybe this peak is even higher. Can't say that right now.
It's not really a question for you, it's just a comment on what Kale said. Yes, there are larger interglacials in the record apart from KM5C, but they're associated with very large orbital forcing anomalies. And the scientific point of Plymouth is to look at something which is more analogous to the future.
So today I'm going to talk about something different from Florian's result. So the title of my talk is Intensified Aridity in Northern China during the Middle Pliocene warm period. So this is a collaboration between my group at the Lanzhou University in China and with Dan Breaker at UT Austin. First, some brief background. So modern world is characterized by a warming climate with high CO2 concentration. The CO2 is about 400 ppm. So one question to ask is, will dryland expand or shrink under a warm climate? The Asian inland arid region is one of the typical region, one of the largest arid region in the world. And so the Lost Plateau is right in the south of this large aridification zone. So if it's going to expand, I would expect the Lost Plateau will be incorporated into this region. So Lost Plateau is a very good site to study, to test to answer this question. So this is basically the same picture as the last one, but with the atmospheric circulation pattern. But since Florian has already done a good job, so I'm going to skip this slide, save some time. So there's different opinions. Opinion one is the dryland will expand. This is based on model simulation. It's based on Jianping Huang's work. They did a bunch of modeling, and the results suggest that intensified aridity with the continual warming. Of course, this is in a short time scale. But the geologic evidence doesn't support this idea. So this is the work by Yang et al. And published in PNAS. They studied the data C13 of organic matter on the Lost Plateau. And what they found is that during the last glacial maximum, the 10% of C4 plant isoland was here. So to the northwest is mostly dryland. But during the mid mid-Holocene, this land advanced 300 kilometers inland towards the dry region. So this data suggests that dry land will shrink. So, but either the middle Holocene might not be an analog for the future climate, because the climate was warmer, and the middle Pliocene period might be a better analog. There's several reasons. First, on the Lost Plateau, the precipitation during the middle Pliocene is similar to the modern condition. If you in this plot. So the other condition is that the early Pliocene, the boundary condition wasn't exactly the same as the current condition, with the Tibetan uplift and the Panama Seaways closure might all occur around 4 million years. So I will argue that the mid-Pliocene is a better analog to the future climate than the early Pliocene. I'm going to look at the red clay sequence on the Lost Plateau, which is a continuous deposit since the late Miocene. As you can see here, the red color is the red clay sequence, and above is the lost Paleozoic sequence deposited during the Quaternary time period. And for the upper sequence, you can see there is a dark layer and light layer. The dark layer forms during the interglacial time period, and the light layer are just lost layers. It's basically they are serve as the parent material, like a sea horizon for soil to develop. The Lost Plateau, the red clay is different. The Lost Plateau doesn't have that color change. As you can see, the color is generally reddish. So their sea horizon has been all modified, so to some degree. So my study site, I forgot to mention, is these stars. And this is a zoom-in picture of the middle part of the Quaternary loss. And this light layer, dark layer, corresponding to Paleozoic and loss, respectively. If you plot the magnetic susceptibility along this section, you will see the high susceptibility during the Paleozoic interval and low susceptibility for the loss layer. This is a better picture of the red clay. As you can see, the red clay is it doesn't have the lost Paleozoic layer anymore, because all the A horizon has been largely eroded. There's no A horizon. So C horizon has been altered to a certain degree. So in my view, that's just a bunch of the B sequence. So the age model. The age model has been established using PaleoMag like 15 years ago by Song et al., and I was part of the team. Now, how do we get the age model? What we did is we sample the discrete sample at a 5 centimeter resolution. Then we measure the susceptibility, which is this curve, versus depth. Then we correlate it with the susceptibility versus age, like obtained 15 years ago. As you can see, the pattern is very easy to make the correlation. So this we got the initial age model. So for the upper part, for the from 3.6 to 2.6, we further fine-tune the magnetic susceptibility to the magnetic susceptibility stack established by Yubin Sun et al. This was based on the same tuning strategy as the Losicki-Riemel stack. So that allows a direct comparison between these two records later on, which is quite important. So with the age model established, I need one way to see whether the Lost Plateau was drier or wetter. So there is lots of pathogenic carbonate. So for formation of the pathogenic carbonate requires evaporation. And of course, there's many ways to interpret the isotopes in a pathogenic carbonate. But I think one I think it's fair to say that with the strong evaporation, you'll have more enriched data O18. So I'm going to using this approach to see the aridification change. Then there's more complexity. So there's two types of carbonate. The one on the left is 1 meter thick, and the lack of the pathogenic feature. So that's, I think, have a complex origin, so might related to evaporation in water or something. So I avoid sampling these intervals. So what I sample is this pathogenic carbonate with the nodules, with the individual nodules can be recognized. So now we can ask questions and test these questions. So if the loss plateau was drier during the mid-Pliocene, the evaporation will be stronger. And here's the result. This is the data O18 of the nodules, and this is the age model. And this is 3.3 to 3 million years. As you can see there's two high peak with more enriched data O18, and these are actually the highest two values over the entire 6 to 2.7 million years. So they're indicating, I interpret this as a dry evaporation condition. And the last interglacial loss data carbonate nodules data O18 is around -7. So this is, if the source hasn't changed, the evaporation was more extreme than the last interglacial. And we are not alone to find this data, the highest evaporation during the mid-Pliocene. So there is this red curve is from Ding and Al in the nearby section. And their record has not been tuned to the basic data O18 yet. But as you can see, this is based on PaleoMag. As you can see, during 3.3 to 3 million years, there is one high peak. If we tune it, this one will align well with our data. So we are not alone. So the second question we can ask is, if the loss plateau was drier during the mid-Pliocene, strong evaporation will occur during the interglacial instead of glacials. So this pink curve is the magnetic susceptibility, and the blue curve is the data O18 of nodules. As you can see, most of the more enriched data O18 aligns with high susceptibility, which indicating wetter condition. So in wetter condition, in interglacial, there will be more evaporation because of the high temperature. And more interestingly, when you compare these two peaks with basic data O18 of Leeds Remo, which is the black curve, and then the brown curve, which is from Zakos et al., they align with the two interglacial time period. So the last question is, are there any other evidence? So if the loss plateau was drier, as suggested by this data O18 curve during the mid-Pliocene, well, vegetation has response. So I would think the tree percentage will decrease during this time interval. So I compiled two pollen data. One is from the northeast loss plateau. The other one is from the central loss plateau. And they actually combine, there is published data about the tree percentage. So without tuning any data, just within the uncertainty of the age model, we found that there's a tree percentage decrease right across during the 3.3 to 3 million years. So again, this suggests that that's consistent with the data O18 data of the pathogenic carbonate. So with that, I'd like to conclude the loss plateau was likely drier during the middle Pliocene, and if future climate resembles the middle Pliocene, the dryland in China might expand southward. Lastly, I'd like to acknowledge Ulrich Salzman and Florian for collaborating with me to generate high-resolution pollen data during the mid-Pliocene on the loss plateau. As you can see, the current record during the Pliocene has very few points, so doesn't allow to answer the orbital time scale vegetation response. I also like to thank Carmi for discussing and Yogui Sung for participating in the field work, and my student from Lanzhou University. This work is funded by NSF of China and the NSF PIRE project. With that, I will end my talk and take any questions.
Just ask about your stratigraphy. So when you're using the paleomagnetic reversals, are you using the most recent magnetic reversal dates? Because since the Sun 2001 paper, some of the dates of these reversals have changed. So have you been updating them?
Oh yeah, that's a good question. I was using the 95, the Candy Can. I haven't done the tuning. Maybe I should. But then we did a tuning. So for the tuning, which has been tuned using the same strategy as Lorraine Remo tuned to the installation. So I think that maybe they can circumvent the old GBTS standard.
Yeah, unless the ages have shifted by more than one cycle, you know. So it would be worth double checking, I think, for some of the
it's a good question.
constraints.
Yeah, thanks.